Welcome, Walter Johnson students. This video will be covering pages 26 to 31 of the Algebra 1B semester exam review packet. So we're going to start with this. It says, for items 67 and 68, determine the side of the right triangle marked X. Now this does not show that it's a right triangle. Oftentimes we have this little box that shows it's a right triangle. All right, and it says, right triangle. I might look back at that first page and see that there's a bunch of formulas. If I don't remember the formula, they're right here. It says Pythagorean theorem. In a right triangle, a squared plus b squared equals c squared, where a and b are the lengths of the legs and c is the length of the hypotenuse. This whole formula sheet will be given to you during the exam, so you want to reference back to it when you need it. So let's write out that formula that we just read. A squared plus b squared equals c squared, and these are the side lengths of the legs, and c is always the hypotenuse. So we can basically plug our values in. If this is our a, this is our b, and this will be our c. So 5 squared plus 12 squared equals x squared. Alright, 25 plus 144 is x squared. Let's add them together. We get 9, we get 6, 169. And to get rid of the square, we're going to square root both sides, right? We can do that on our calculator, the square root, or we think what times what gave me 169? And we get 13. Now, when we take the square root of both sides, there's a plus or a minus, but in this case, because it's a distance, we're just going to look at the positive version. So x equals 13. So that is the length of our hypotenuse. Over here, it's a little different because we know the hypotenuse length. So that could be our a squared plus b squared equals c squared. So we have 100 is going to equal 49 plus x squared. All right, we want to get x squared by itself. And let's see, we're left with 51. Ooh, that's pretty far away. Okay, x squared equals 51. Square root both sides again. Now this one does not come out as an even number. An exact answer would look like this. It is exactly the square root of 51. That's our exact answer. If we approximate it, x is about, well, it's close to 49. 49 is 7. It's a little bit more than 7. 7.14. We could just type that in our calculator. Let's just look real quick. We would go, we would type in second square root, this little guy right here, of 51, and that would give us our approximation. And we rounded, so we put these little squiggly, which means about. All right, so that would be our exact and approximate answer for number 68. All right. 69 and 70. Find the distance between each pair of points. All right, so we also have something called the distance formula. Now, as I taught it, you don't have to use the distance formula. You could say, if I want to find the distance between 7, -2, right here, this point right here, and -6, 3, you could make a right triangle, and you could do it either way. You could do it above or below. So I'm going to do it below and say over and up. Right, can't go past. So we could then count this side and count this side, and that's a right triangle, and then basically we have a squared plus b squared equals c squared. So that is one method that you could do. I'm going to do the distance formula method though, in case other teachers were emphasizing that. So this is our x and our y, our x and our y. This is, we want, one of them is our first, and one of them is our second. And it doesn't matter, we could do this is our first, this is first, this is second, or this is second, this is first. It really doesn't matter. So the formula is on our formula sheet. Let's find that right here. It says the distance between 2 points, x sub 1 and y sub 1 and x2, y sub 2 is the square root of x2 minus x1 squared plus the quantity x2, y2 minus y1 squared. All right, so we can use that formula to solve this. So I'm going to go ahead and take away the graph because we don't need it for this so much. So the distance is going to equal the square root of, I like to set it up so that it's ready. Like, all right, everything is there. I'm going to do x2 minus x1 right here. So x2 negative 6 minus 7. That's x2 minus x1. In a different color, I'm going to do y2 minus y1. So I'm going to take 3 minus a negative 2. We have to be really careful with that minus a negative because that's going to become a positive. So here we end up with negative 13 squared plus 5 squared. Alright, so where were we? Let's see. We were taking the square root of that squared plus that squared. Alright, so be careful. 3 minus a negative becomes plus, and you got 5. Alright, 13 squared is 169. We just figured that out a minute ago. Plus 5 squared is 25. And we still have the square root. We're still equal to the distance. And let's see. Add those up. And we get the square root of 100, 60, 70, 80, 94, the square root of 194. So that is our exact answer, and if we type it into our calculator, we will get that the distance is about 13.928. So that would be the answer for this guy right here. All right, let's do it a little bit more abbreviated. So we have room. Okay, so we've got, or I could just use white. Here we go. x2 minus x1, 2 minus a negative 6. Did you guys see how I did that? Minus a negative. I made the minus a negative into a positive. All right, so we have 8 squared. And then 9, let's use a different color. 9 minus 3. I know that. 9 minus 3 is 6. 6 squared. Alright, switch to white so we can see. D is the square root of 64 plus 36. Add those up. 6 and 4 is 10. That's 9, so 90 plus 10 is 100. Ah, that's so nice. So the square root of 100, I wouldn't want to leave it like this because I could simplify and get an exact answer of 10. So the distance between those 2 points is 10. Alright, so technically I didn't have to look at the graph. But if you wanted, if you had extra time, you might want to go back and double check, count, draw the triangle. You could always double check your work that way. All right, hope that was helpful. All right, next one. Which graph below represents the function of f of x equals absolute value of the quantity x plus 3? So when we were doing quadratics, we did a lot of shifting right and left and up and down, and the same patterns apply to all different types of functions. So because this is on the inside, oops, still writing in white. Because this is on the inside, we're going to do the opposite. So this is our right and left movement. It's either right or left, but we want to do the opposite. So if it says plus 3, I'm not actually moving right 3. So this is tempting, but it's not the right one. I want to do the opposite of right 3. I want to go left 3. So it looks like this one's going to take me left 3, right? So that, I guess we could call that the vertex, the minimum of our absolute value. In this case, it's going up and down, so it's checking. Do you know that that's supposed to take my function and move it left 3, right? So because it says plus, we're not going to the right, we're going to the left. All right, so I would say A is the answer. Ah, what could we do? We could actually type it in. Let me go type it in. Let me turn this one off. Enter. Oh. Enter. That turns it off. Okay. In magenta, let's go and type in the absolute value. Math. Over here, if you go to number, you can type in absolute value. Enter. Absolute value. Where is it? Didn't want to do it. Huh. Math number 1. I don't know why it's not showing up. X. Huh, my calculator's having an issue here. Let's try this one more time. Math, number, absolute value. There we go. All right, of x plus 3. Now you may actually have ABS. It might say ABS. On this one, it's a fancy one, the newer one, so it is just showing x plus 3. So I can go ahead and type that in and hit graph. And then I can easily match and say, oh yeah, that definitely looks like this one. It moved left 3. All right, so use your resources. If you have your calculator, check your work. All right, next one. This is a fun one. Let's see. I don't know what happened here. Move that out of the way. Okay. We're having all sorts of exciting stuff happen. Sorry, guys. All right. Jill takes a Sunday drive in her car. She drives at an average speed of 50 miles per hour for 3 hours. She takes a dinner break for 2 hours, and after dinner she travels at an average speed of 25 miles per hour for the next 4 hours. Let t represent the number of hours since she started, and I see that right here, so this is hours since she started. And let d of t, which I see right here, represent the total distance that she's traveled after t hours. So this is distance, I imagine, in miles, because she's doing miles per hour. So total miles, right? Total. It's always a good idea to label your axes. All right. So the first question is, what is the domain? So this is saying what values of t are we using? So where did we start and where did we stop? Well, we started at 0, and then she started driving for 3 hours. And then we stopped for 2 hours, and then she kept traveling for 4 more hours. So 3, 4, 5, 6, 7, 8, 9. It sounds like from time of 0 to 9, we were in the car traveling. Oh, or stopped for food. So any time between 0 and 9 hours, another way to write that is from 0 to 9, including 0 hours and including 9 hours. So this says t's less than or equal to 9 or greater than or equal to 0. All right, now we want to sketch it. All right, let's sketch it. Well, let's see. She starts at an average speed of 50 miles per hour. At the beginning, she hadn't gone anywhere. After 1 hour, she went 50 miles. After 2 hours, she went another 50 miles. After 3 hours, she had gone another 50 miles. So we could make a t-chart. Oops, t and distance. So after 1 hour, she'd gone 50 miles. After 2 hours, she'd gone 100 miles. After 3 hours, she'd gone 150. So there's a couple ways you could approach this. So this is what's happening on her first driving experience. Right, and then she decides, all right, then I'm going to stop and take a break for 2 hours. Does she get further while she's sitting in the restaurant? I don't think so. So she is going to stay at 150 miles for 2 hours while she eats between 3 and 5. And then she stops. Then she decides, I'm going to get back in the car. So when she gets back in the car, now she's probably on little roads, not on the highway, so she's going only 25 miles per hour. So in 1 hour from 5 to 6, she's only going to travel 25 miles. So from 150 to 175. So this, and then over 1 more, up 125 miles more, 1 hour more, 25 hours more, and she does that for 1, 2, 3, 4 hours. All right, so that's what our graph would look like. Sketch a graph of d of t on the coordinate axis below, and there it is. All right, write a piecewise function for d of t. So what would an equation look like? Now we have 3 parts, right? I'm going to color code this just so that we can kind of keep track. So we always want to write d of t on the outside, and then we put like a little bracket so that we can hold all of our pieces. So the pieces, this is our y equals, so we don't need another y equals in here. What does y equal? Y equals something, comma, if, and it's only on a certain time. From time 0 to time of 3. So all my pink is happening between 0 and 3. So here I'm going to have time of 0 to time of 3. Less than or equal to, less than or equal to. So all of this from time 0 to 3. What is my function? Well, I'm increasing at a rate of 50 miles per hour. Where did I start? I started at 0, so increase 50. I might want to test, plug in a 1. And I'm 50. Yep. If I plug in 2, I'm at 100. Yep. All right. So we're okay with that one. The second equation is just a flat line, right? we stay at 150. It's not changing at all. So y equals 150. It just is what it is. If t is between 3 and 5, right? So we stop for dinner between 3 o'clock and 5 o'clock. So for 2 hours, we're stopped. And since I already made t equal to 3, I'm not going to make it equal here. I'm just going to say when t is greater than 3 or less than 5. And then once it hits 5 o'clock, she's like, oh, let's get back in the car. All right, now this is the exciting one to do. So let's look at this. I'm going to zoom in a little bit. Okay. Oh, that was too much. No, I'm going to have space. Okay, I'm going to write little ink. So if my time starts at 5 and goes till 9, right? And we're including 9 and we're including 5. We didn't include 5 there, so we'll include it here. All right, technically, if you included it both places, it wouldn't be that big a deal because you're at the same spot. But mathematically, it's a good idea just to have it on one or the other. Okay, so for this one, we want to say, where did we start? We started at 150. And then she increased at a rate of 25 miles per hour. 25 miles per hour. But instead of saying per hour, because this says my y-intercept is 150, but I'm not back here, I'm all the way over here. We started 5 seconds later. I'm sorry, not 5 seconds, 5 hours later. So we want to put in here t minus 5. 5 hours later, she was at 150, and her rate of speed was 25 miles per hour. So that would be a good equation for the red line. And the last question is asking, what was Jill's average speed? Well, average is the sum divided by the total. So the sum, so what is the sum of all the distance that she traveled divided by the hours that she traveled? So the total distance, and it looks like in total, with all the traveling, she got up to 250 miles. So she traveled 250 miles. It's always good to put units, that'll help you. And she traveled 9 hours. So if we divide those two, we can find the average rate of speed, miles per hour. The units help me. If I accidentally put hours on top, I'd say hours per mile, and I'd say, what? Hours per mile? That doesn't make sense. Miles per hour. So 250 divided by 9 is, well, it's about 27.8. So miles per hour. Her average speed was 27.8 miles per hour. So she had to deal with the 0 miles per hour. That really pulled down her speed. She had 50 for 3, then 0, and then 25 for 4. All right. Hopefully that helped you work on that piecewise function. All right. Another one where it's asking us to write the piecewise function. Let's read the problem and see what it's asking. All right. Bob uses sugar to make candy. Beginning at noon, he uses sugar at a rate of that many pounds per hour. At 3 o'clock, he uses the sugar at a rate of 50 pounds per hour. He stops making candy at 7. Let t represent the number of hours since noon. Let s of t represent the total amount of sugar that Bob used after t hours. Between noon and 7, what is the total amount of sugar that Bob uses? All right, well, I'm going to plot this out. I'm going to say at time 0, 1, 2, 3, 4, 5, 6, 7. That's going to help me because I know that he went from 0 to 7, from noon to 7 o'clock. And in the beginning, it said he used 100 pounds per hour, and then at 3 o'clock he changed. So from 0 to 1, for 1 hour, he was doing 100 pounds per hour, then another 100 pounds per hour, and then another 100 pounds per hour. So in that 1 hour, he used 100 pounds each of those hours, so it was 300. All right, and then he starts using 50 pounds per hour until 7. So 50, 50, 50, 50, and then he stops, right? So I would count these up, 1, 2, 3, 4, 5. So 500 pounds of sugar. Wow. All right. On the coordinate grid, make a continuous graph. That just means connected. showing the total amount of sugar that Bob uses as a function of t. Similar to what we did last time, after 1 hour he's used 100, after 2 hours he's used 200, after 3 hours he's used 300. We can connect those dots in a line, and then he changes to a rate of 50. So here, in 1 hour, he only increases 50. Another hour, only 50. 50 and 50 for 4 more hours until we get to 7. So that would be the graph. One rate changed to another rate. All right, and then the last part is asking us to write a piecewise function, similar to what we just did. Here, for the first 3 hours, he was going at a rate of 100 pounds per hour. But then here, right, we started at 300. Let me zoom in a little. We started at 300, and we increased at a rate of 50 pounds per hour, but we started 3 hours later, right? This rate started 3 hours later, so we are going to go t minus 3. All right, that's what they're looking for. All right, this is asking which statement is true about this function. So I went over here and I graphed it. If I go and turn on my graph, then we can look at it. Let me go turn off the absolute value graph and graph it. All right, this is our absolute value function. You know what? I think that I can take this and drag it. Woohoo! All right. Oops. That's my lesson for today. So, looking at this, we're asked about domain and range. So first is, I'm given a function, let me graph it, let me look at it. Both the domain and range are all true. I'm sorry, which statement is true about the function? Both the domain and range is all real numbers. Does this function cover all my x's? No. Does it cover all my y's? No, because it doesn't go all the way down. So I know that this is not going to be it. All right, both the domain and range is all real numbers greater than or equal to 0. So here's 0 greater than, yes. And this is 0 greater than, yes. As long as it says greater than and equal to 0. Yes, I agree with that one. Let's just double check the next two, because sometimes you're going to have things, maybe not on the final exam. But it's good idea to check and make sure you don't think two are true. The domain is all real numbers. The range is all real numbers greater than or equal to 0. No, we already decided the domain can't be all real numbers. The domain is all real numbers greater than or equal to 0, but the range is all real numbers. No, not possible. So neither the x or the y goes all the way. So it has to be B as the answer. All right, 75. Okay, so we have a graph of, this is like the floor, this is a step function, right? Some people call this the floor function and the ceiling function. So we have 4 different statements that we have to decide which of them is true. So if we look at the first one, for every value of x, if x is 1, if x is 1.1, any value of x, let's say if x is 2.3 or if x is 2, all of those values, the floor function is going to be greater than the ceiling function. Well, right off the bat, if something's low, is that going to be bigger than if it's high? Not really. So let's test a value. If I plug in 2.3, 2.3, is that greater than this guy, 2.3? Well, this one says round down to 2. Is 2 greater than this one says round up to 3? Is 2 greater than 3? No, that's not true. All right, and then if you notice, this same exact statement is over here. So these two, I think, are not true. Then we ask, okay, well, for every value of x, if I plug in 2.3 here, 2.3, oh, we already did it. But instead of a greater than, it's a less than. Is 2 less than 3? Yes, that's a true statement. But it says for every value. So one value and testing it isn't enough. Let's try another one. What if I just plug in 2? 2 is less than 2. So this, if I round down, I get 2. And this, if I round up, well, there's nothing to round. Is 2 less than 2? Well, not really. 2 is equal to 2. So if I have an integer, this statement is not true. But for an integer, that means if I just plug in a 2, then they're equal. Otherwise, the floor function is going to be less than the ceiling function. So this one would be our correct answer. D is the correct answer. All right, so for problem number 76, it's asking us to graph a piecewise function. So I'm going to encourage you to make 3 little tables. So we're going to label them x and f of x, x and f of x, x and f of x. Your teacher might have done a different strategy, but this is what I'm going to encourage or suggest as a strategy, especially if these are tricky for you. Okay, so we have 3 different sections. This one says f of x equals 3, right? No matter what x is, it equals 3. But in this, it's only if x's are less than -4. So I want to start with -4 when x is -4 or less. What's a number less than -4? Maybe -5. Okay? No matter what, it's 3. The y is 3. Doesn't matter what the x is. Well, if the x is -4 or less, the y will be 3. But because it's not equal, I'm going to have an open circle. So at -4, 3, I'm going to have an open circle, and then I'm also going to have that one. But any one that's less, -6, -7, all of them are going to be 3. So we're just going to have a straight line going across that way. If it's in the middle section, now our y, how we get our y is we plug into that. And it starts and stops. It starts at -4 and stops at 3, and I want to do one in between. So I'm going to do 0 in between because that's the easiest. So I plug in a -4. 2 times -4 is -8. Okay, so I'm plugging in 2 times -4 plus 1. Well, that's -8 plus 1 would be -7. So my point, -4, -7, -4, -1, 2, 3, 4, 5, 6, 7 is right here, and it's a solid dot because it says equal to. All right, at 0, I plug in 0. 2 times 0 is 0. 0 plus 1 is 1. 3, plug it in. 2 times 3 is 6. 6 plus 1 is 7. So 3, 7. So 0, 1 is a point, and 3, 7. So that right there is my middle piece of my piecewise function. Then I can do my last piece, which is -5. Y equals -5. No matter what my x is, the y is -5, -5, -5. What are my x's? Well, x's have to be greater than 3. I want to have 3. I know it's going to be an open circle. I want things greater. 4, 5. So these are my points. 3, -5. Open circle. 4, -5. 5, -5. Keep going. 6, 7, 8, 9. All these numbers are greater than 3. So that is the example. That's what our piecewise function would look like. For this one, this is just shifting us right or left. Kind of like we had the absolute value of x plus 3 earlier. We plugged it in the calculator and we saw that it really moved left 3. Same thing with this. It's taking a square root function, which looks like that, and it's shifting it 1 space left. But I could pull up my calculator, go to my y equals, and go and graph it. So I'm going to hit that, enter, go down, hit enter. I can graph it and see, yes, it's right there. If I want to know what the values are, I hit second table, and I can look at my values, 0, 1, 0, 1. I actually want to go back a little bit further. So if I go up, I can see -1, 0. Notice there's error, error, error. That means there is no function on that part of the domain. So all these x's are not included in that function. So -1, 0, 1, 0, 1. Those were 2 points. If we keep going, 3, 2. Let's find one more. 3, 2, and 8, 3. 3, 2, and 8, 3. So that would be the graph of that function. Alright, and this last one is saying the cube root function, and we're shifted up 2 because it's on the outside, it's up 2. So it would be on the inside if it said x plus 2 on the inside. That would be right or left, but this one is up or down because the cube root stops. So again, I'm just going to go to my calculator and plug it in. I've actually already plugged it in, but I think I should show you how, right? Because this one's a little trickier. Okay, so let me delete this. Okay, in order to get the cube root, here, why is it not clearing? I just have to go there, right? Clear. There we go. Okay, so in order to get cube root, we go math. So the math button takes me to this cube root. So math 4 will get me the cube root, and it said cube root of x. And then outside, so I have to go to the right to make sure I'm outside, and hit +2. I just realized my microphone was way up by my ear. I hope you could have heard me. Alright, so we went to math, cube root, which was 4. Went to math 4, put an x, move to the right, and hit +2. So this is the only one that's going to graph right now. I'm going to hit graph and see what it looks like. It's my cube root function, and it shifted up 2 spaces. Normally that little turning point was at 0, but it shifted up 2. Okay, so I can look at my table and look for points that I can plot, and I see some points right there. So if I go back a little more, oh, there's one. Okay, -8, 0. You could just make a list, -8, 0. That's one point I can plot. Then we've got -1, 1, 0, 2, and 1, 3. And then I believe there was one more, something 4. And I believe it was 8, but let's go check to make sure. Sorry, oops, we don't need to see all that. All right, if I go down, six, 7, 8. There we go, 8, 4. Okay, so great. Now we can graph it. Since we have all these points, we can go to -8, 0, -1, 1, 0, 2, 1, 3, and 8, 4. So it comes in like this, turns around, and goes like that. So that would be the graph of a cube root function. All right. Over here, last 2 items are just asking us to evaluate. What if I plugged in 1.6 and did a floor step function, right? A floor function. Well, I just round down, so 1.6 rounded down will be 1. And if I took 1.6 and I rounded up, well, that would be 2. And then here I have to decide, where does 1.6 go? Is 1.6 greater than 2? No, it's not. So we're not going to use this part. We're only going to use this one, x's that are less than 2. So we're going to plug in 1.6. So I'm going to do the cube root of 1.6 plus 6.4. I just plugged in my x value right there. Add them up, 7, 8. The cube root of 8 is 2. So when x is 1.6, f of x is 2, or f of 1.6 is 2. And that would be your final answer. Alright, I hope this video was helpful for your final exam review studying. Alright. Thanks for watching.